Hi. Hi, can you hear me? Okay? Well, it's going to be hard to follow that. That was really the summary of everything I wanted to say. But I'll try. It's a real pleasure to be here. This is an amazing event, an amazing venue. I just flew in this afternoon, and this is waking me up already, so that's good. So I hope to have fun tonight and tell you a story that will change maybe a little bit of your perspective of the place or your place in the universe. This, by the way, is the universe, in case you wondered. This is a picture from the Hubble Space Telescope. And every dot in this image, except for that one, is a galaxy, not a star. There are 100 billion galaxies in the observable universe, each containing 100 billion stars, and we're on just one of them. And even that is an amazing discovery. I won't have time to talk about that. But 100 years ago, we thought there was one galaxy in the universe. We now know there are over 100 billion. And that just gives a sense of how things are changing. And every day we discover new and amazing things about the universe. And what I want to talk about is how it's not just out there, how you're connected to the universe in ways you may never have imagined. But I want to begin this story as a story. So, like good stories, I want to just say at the beginning, it's the best of times. And by that, I mean that the Large Hadron Collider is operating in Geneva and has not created a black hole that destroyed the world. So that's very good. But at the same time, it's the worst of times, as we've seen in that last video. And the important thing about cosmology and science is it can take us away from these local awful things, because this too shall pass. This is just a speck in a cosmic history. So as miserable as this may be, it's just a moment. And so anyway, let me begin by taking you first to a connection that was talked about in the video a little bit, but maybe put a little more content than just the fucking. So I like art, and it's great to see art here, and it's wonderful that there's an artist doing this right now, even as I speak. One of my favorite artists is a sculptor, Rodin. And I was in the Rodin Museum in Paris once, and I started to think about something. I later wrote a book about it, about the fact that when you look at Rodin's art, there are beautiful moments that are captured. And there's a famous statue that Rodin has of a kiss. And I was looking at that, and thinking that kiss was immortalized in stone forever. But of course, it's not forever. And the stone hasn't been around forever. The stone has only been around for millions of years. And I started to think about what is forever? What's eternal? Is there anything that's eternal? And nothing is. But the closest thing, of course, in some sense, is our atoms. And our atoms have been in a lot of interesting places. I have my cocktail here, which unfortunately is empty and no one has refilled it. But in any case, maybe that would be a message to the people. I was getting that one that bubbles, if you want to bring me another. But my mother used to tell me when I was a kid and I picked up a glass, she said, don't touch that, you don't know where it's been. And she will be amazed by the real true story of every atom in your body. Because every atom in your body, as I say, is just been around on Earth for 4.5 billion years, but it's been around a lot longer than that. And in fact, the actual atoms have not been around since the beginning of time. In the beginning of the universe, there were only hydrogen atoms and a little helium and some lithium, which is important for some of you, I guess. But for the rest of us, the carbon, the nitrogen, the oxygen is the important stuff. And that hasn't been around for a long time. And the first connection I want to bring you is your connection to the cosmos. What do you know? Is this one of the ones that bubbles? Okay, good. Okay. Not the same one, but it'll do. It's a little stronger. Okay. The talk may go on longer than I intended. But so this was the first thermonuclear explosion on Earth. It was the Mike explosion in 1952, November 2nd at 7 in the morning, I think. And briefly, of course, it wasn't done as a science experiment. It was done as an experiment to destroy things. And great. Okay, here we go. Okay, well, I'm going to have my work cut out for me. Okay, I'm not responsible for what I do after those. Okay, so it destroyed a Pacific atoll in a microsecond in this thermonuclear explosion. But interestingly enough, in that microsecond, every element that was ever existed in the universe was also created, because thermonuclear explosions involve nuclear fusion, and that's the process that powers stars and the sun. And that's how your atoms came to you, because the carbon, the nitrogen, and the oxygen, the iron, was only created in the cores of stars. It wasn't created in the Big Bang. And the question is, how did it get to your body? And it got to your body thanks to stars, and stars that exploded. This is an image from a nearby galaxy, about 70 million light years away. And it's a galaxy just like our own. If this were the Milky Way, we'd be sort of located sort of there in a boring suburb, not Christiana or anything, but where the Earth is around, and the sun is around our galaxy. But this is another galaxy, and what you notice about this galaxy of 100 billion stars is there's maybe 10 billion stars in the center, but you notice this bright star here. And this star is shining with the brightness of the entire center of that galaxy, which is surprising, because there are 10 billion stars in there. So the first thought you might have is that this star is just in our galaxy and it got in the way of the picture. But that's not true. It's a star at the edge of that galaxy, and it's shining with the brightness of 10 billion stars. Why is that? It's a star that's just exploded, a supernova. An exploding star, the brightest cosmic fireworks anywhere. When a star explodes, it shines brightly for about a month with the brightness of 100 billion stars. And stars end their lives, some of them, as exploding stars, and it's important for us that they do explode, because if they didn't, we wouldn't be here. Because all the nuclear materials that are produced during the lifetime of that star are then sent out into space. Now, we actually can observe exploding stars. Fortunately for us, stars don't explode too often, once every 100 years per galaxy. Fortunately, they explode, however, because if they didn't, we wouldn't be here. Now, how can we observe stars if they explode only once every 100 years per galaxy? The answer is the universe is a big and old place, and rare events happen all the time. I'll stand for you to finish that picture, and then I'll move. Okay, good. Anyway, so once per 100 years per galaxy. Well, there's two ways we could study it. First, we could assign a graduate student to each galaxy, because 100 years is about the right time for a PhD, so that's okay. And you know, if the graduate student dies, it's okay, because students are very cheap, so that we don't need them. But there's another way, and that is to realize that, okay, because the universe is big and old, these events are happening all the time. And tonight, you won't be able to see if it's cloudy, but if it ever gets clear in Copenhagen at night, you could take a small hole with your hand and look up at the sky where there are no stars, and take a hole that big. And with the largest telescopes in the world we have in Chile, if you looked up in that dark spot, you'd see about 100,000 galaxies in that little region. And that means if you look at 100,000 galaxies in a given night, and you work things out, once every 100 years per galaxy, you'll see a few stars explode. And astronomers do that. They apply for telescope time, and they look out, and if they can see enough galaxies on a given night, they'll always see a star explode. And we can study those stars, and we've been able to learn about them, and we've been able to use them to study the universe. That's in some sense a different lecture. But these stars, when they die, they create other star systems. This was, by the way, the most recent supernova that we've seen, not in our galaxy, because the last supernova that was seen in our galaxy was about 400 years ago. And amazingly, the reason for that is because most of our galaxy is dust, and we can't see the exploding stars in our galaxy. They get obscured by dust. But if we look at other galaxies, we can see them. But this one was in a neighboring galaxy, the Large Magellanic Clouds, which is, you can see in the southern hemisphere. And this star exploded in February 1987. And there are other stars that have exploded. This is the Crab Nebula. There was a star that exploded about 1,000 years ago that was seen that could be seen during the daylight on Earth when a star explodes in our galaxy. And it's interesting to me to think about this because this was in 1060 something, I forget the exact year. But there's no records in Europe of that star exploding. Yet in China, there was a record. Chinese astrologers saw a guest star in the sky and reported it to the emperor and said it brought good tidings, because of course that's what the emperor wanted to hear, which is what religion's all about. But it wasn't recorded at all in Europe, and I think one of the reasons was also religion, frankly, because the conventional wisdom in the Christian church was that the sky was not only God's creation, but it was immovable and unchangeable. And if you said you saw something new in the sky, you'd likely be burned at the stake. So it's not too surprising that it was never reported here. But this was a nearby supernova. But interestingly enough, here's that supernova from 1987, 20 years later, and you can begin to see a ring around it. I think I'll expand it. This is the material that's being thrown out by this star, all the carbon, the nitrogen, the oxygen, the iron, moving at about 10,000 kilometers per second. And when stars explode, they compress the gas around them and cause it to shine, but they can also actually cause other stars to be created. This is not a painting. This is an actual image of a stellar nursery in our galaxy, where after a supernova goes off, it compresses the gas and other stars form. And about 5 billion years ago, a supernova went off in our region of the galaxy, compressing the gas and causing our sun, what is now our sun and solar system, to eventually form 4.5 billion years ago. And the material from that supernova not only became part of the sun, but it eventually became part of the Earth and all the other planets. And every atom in your body, as said in that video, but it's true, and it's the most poetic thing I know about the universe, every atom in your body has been inside a star that exploded. But not just one star, many stars. Because in order to make up enough carbon and nitrogen and oxygen, lots of stars have had to explode. 200 million stars in our galaxy exploded before the sun formed. And so the atoms in your body have been part and experienced the most violent thing in the universe. And the atoms in your left hand could have come from a different star than your right hand. But you were literally star children. And I think that's a wonderful way to begin this, because you have a connection, an intimate connection to the cosmos. It's not just out there, it's in your bodies. And your bodies provide us living histories of the history of the universe. You like that? Okay, you can applaud for that. We come from the stars, but I want to come a little closer, and I want to talk about another connection that you have that you may not know about. First of all, this is a picture taken, a nice sunset. It looks like it's Los Angeles, because the sky is red from used to be pollution. But it's not. That sunset happens to have been taken on this place here in Mars. Now, Mars is interesting to us because Mars is a dry planet now, but we think it originally had water, as I'll show you. And the interesting question here is, first of all, we used to wonder, where did the water on Earth come from? Earth is a water planet, but when the Earth formed, the temperature in the solar system in the region of the Earth was about 1,000 degrees, so it was hard for water's a volatile material. And it turns out that if you work out, we're being bombarded by comets, asteroids, meteorites every single day, in one form or another. And if you work out over the history of the Earth, enough material has been transported to the Earth by comets to fill up all the Earth's oceans. So we thought for a long time that maybe that's where the water comes from. But there's a problem. If you measure the content of the water in comets and measure what's called the isotopic abundance, the abundance of hydrogen and the next lightest, or the heavy hydrogen called deuterium, it's slightly different in the comets than it is in the oceans on Earth. So we didn't quite know where the water came from. Maybe it was embedded in the Earth originally. To understand that, we actually look at Mars. Because Mars, unlike the Earth, doesn't have plate tectonics. It doesn't have volcanic activity. Most of the material on the surface of the Earth now wasn't always there because the Earth is churning and that material goes inside and outside. So there are very few very old rocks on Earth. But in Mars, the material that's there has been there since essentially the formation of the planet. And if we could find water on Mars and measure its abundance, we could learn about the water on Earth. But in the process of that, we learned something interesting. The question is, where can you go to find rocks from Mars? You don't have to go to Mars. You go to a place that looks like Mars. That's this place. This is Antarctica, the South Pole. Now, why would you want to go to the South Pole to look for rocks from Mars? Anyone have an answer? What? I'm sure I'm getting lots of good answers, but I can't hear them all. But okay, the point is, it's not very sophisticated. Notice that this is white. Okay, and so it turns out material gets kicked out of Mars by meteors and comets, and some of it falls to Earth, and some of it falls to Earth here on this part of the planet. But if you find a rock out there, it's not very surprising. But if you're in Antarctica and you are on a skidoo near the South Pole, and you're going along the ice and you see a rock, there's only one place it can come from, up there. So that's why we look for meteorites in Antarctica. It's not because of anything sophisticated. They're just easy to find. Anyone could do it. I was going to go do it. And if they wanted me to do it, anyone could do it. And interestingly enough, in this area, the Allen Hills of Antarctica, about 30 years ago, this particular rock was found on the surface of the ice, and it turned out to have the abundance, have the right elemental abundance that we know it came from Mars. And then it caused a great furor about 20 years ago when it was cut into small pieces and put in an electron micrograph. And when that was done, these things were seen, these small structures. And President Clinton at the time had a press conference because these look just like the oldest fossils of life here on Earth. And it was thought that maybe this was evidence of life on Mars. Now, it turns out in the interim, we've been able to show that that's not the case, that these structures are actually much smaller than the earliest fossils of life on Earth, gotten from Australia, as it turns out. And we think that you can create these kind of structures without biological systems. But we've realized in the interim something very important. All throughout the Earth, we found forms of life that exist in extreme environments. They're called extremophiles, and they can exist in boiling water and acid. But interestingly enough, those microbes can live in rocks for a long time, even in dry and extreme environments. That means that if there were microbes on Mars embedded in rocks, they could easily survive the 8 or 9 month voyage through space till they got to the Earth. And that means that no planet is an island. It means if there's life in one place in the solar system, it's going to pollute the rest of the solar system, at least all the accessible places in the solar system. So, the interesting question is this. Life evolved on Earth, and I can still use that word, especially since we're not in the United States. Life evolved on Earth about as soon as the laws of physics allowed, about 500 million years after the Earth formed. I'll have a ways to go. Anyway, because before that we were being bombarded by comets and asteroids and the oceans were being evaporated, but then Jupiter formed and basically ate up most of that material and things subsided. But life formed on Earth extremely quickly. And the question is, that's a surprise to us. How did life originate on Earth? We don't know the answer, although we're getting close. But maybe it didn't originate on Earth. Maybe it originated on Mars and was transported to Earth. Because early on in Mars, it was hot and wet. So if you want to know what a Martian looks like, just look in the mirror. Perhaps. Now, we don't know if that's the answer, but interestingly enough, we've discovered, as we've explored Mars and the surface of Mars, evidence with our rovers, which are a wonderful way to explore the planet, in my opinion, better than humans, but we can talk about that. But we've discovered evidence of, even today, water flows systems that look like there is actually liquid water today still on Mars periodically. And that's incredibly exciting because not only will we be able to study that water, but it gives us hope that maybe we'll find evidence of extinct or maybe extant life forms on Mars. But we don't have to go to Mars. We can go to the moons of Jupiter and Saturn. This is Enceladus, a large block of ice, which 20 years ago we just thought was a perfectly smooth white snowball. But we've now discovered with the Cassini satellite, the Cassini mission, which explored Saturn, Enceladus is a moon of Saturn, that the ice isn't smooth at all. And in fact, there are water flumes and plumes that come up, water volcanoes if you want, because the gravitational pull of Saturn is enough to produce tidal forces that heat up inside Enceladus. So Enceladus and Io are two ice moons that we now understand are not just ice moons. Inside of them is a water ocean, heated by the gravitational force of the big planets they're around. And when the Cassini satellite flew through these, it detected what looked like maybe organic materials. And this material has been protected by a thick wall of ice, maybe several kilometers thick, and then there may be an ocean underneath that's 100 kilometers deep. And one of the exciting things we're going to do, and maybe in the next 2 decades, is send a mission to either Io or Enceladus to maybe explore the surface and ultimately drill down. And we may discover life here, because all of the things that are important for life on Earth, water, organic materials, and sunlight, are prevalent not just here, but everywhere in the universe. We've discovered organic materials, the basis of amino acids, on comets. So it could be that we're not only not alone in the universe, but we're not alone in the solar system. Now, there aren't intelligent beings there, but there could be microbes. And if there are life forms inside of Enceladus, those are exciting. If we discover life on Mars, that could be our cousins, because we've been sending material back and forth by comets. But if we discover life deep in the oceans of Enceladus, that material's been protected, and that could be another genesis of life. And that would be very exciting, because if we find 2 independent geneses of life in our solar system, it means it's everywhere in the universe. But ultimately, we are connected in one way or another to life in our solar system. So we are not just, if we discover life on Mars, as I say, it's our cousin. So we're not just connected to the stars, we're connected to the other planets, and we could be Martians. So that's the next cosmic connection I want to make. So we're connected to the stars, we're connected to potentially life on other planets, but we're connected to each other in a way that you wouldn't maybe not imagine. I want to do an experiment. I want everyone to take a deep breath and then hold it in. Okay, 1, 2, 3. Take a deep breath, hold it in. You can't laugh while you're taking a deep breath. Keep holding it. Keep holding it. Okay, let it out. There was no reason for that. I just wanted to see if you'd do it, but there sort of is. Every time you breathe in, you're being connected to all of humanity throughout history. Who's this? Does anyone know who this is? Julius Caesar, that's right. The amazing thing is, and it's one of the things I love to teach in an undergraduate physics class, every time you take a breath, you're breathing in atoms from the dying breath of Julius Caesar when he said, "Et tu, Brutus." Every single time you breathe, you're breathing in atoms from Julius Caesar's dying breath. It's amazing, but it's true. His atoms of his breath were circulated throughout the atmosphere, and because of the processes that circulate things through the earth and the atmosphere and life, we can actually calculate that maybe 10 or 20 atoms of his dying breath are in each of your breaths. But that means not just Julius Caesar, but that means everyone throughout human history. People we think of as scary, as others, are a part of us. They're not just others. They're part of our bodies right now. Okay, good. This is a Great. This clearly resonates with people who are stoned. Okay. Anyway. But this is useful. Think of that. Think of this the next time you breathe in. But I mean, I use it all the time. I spend a lot of my time, I try when I can work, which is increasingly rarely, mostly on planes. But if I'm alone at night and I'm working and I'm not getting anything done, which is also usual, I remember that each time I breathe in, I'm breathing in some atoms that Einstein breathed out when he put the final dot on his general theory of relativity. So this is wonderful. You are breathing in atoms from virtually almost everyone who ever lived, the good people and the bad people. You're also breathing in atoms from Hitler when he put the last note on Mein Kampf, okay? And speaking of what my mom said, well, I guess I can say this here. So when you drink a glass of water or alcohol, you're drinking in atoms excreted by every slimy thing that's ever walked the earth. In particular, and this is really interesting for some of you, if you have water, take a drink right now. Or even alcohol, take a drink right now. Every time you drink a glass of water, you're drinking in atoms from the sweat of your parents during their coupling that created you. Okay. I remember the American comedian W.C. Fields. I never said this before on a stage, but this place it seems okay. I remember W.C. Fields used to say about water, he said, "Water, I never drink it, fish fuck in it." And now you know it's true, you're drinking it when you come in. And every time, here's a yacht younger me. This is Lucy, who was a wonderful ancestor of ours 3.2 million years ago, Australopithecus, Lucy, who we found. And every time I'm breathing in atoms that Lucy breathed out. But it's not just Lucy, these are stromatoli. These are the earliest, this is from Shark Bay, Australia, which you can see here. These are fossil remnants of the earliest organisms that produced oxygen on Earth. The cyanobacteria that originally there was no oxygen in the atmosphere of the Earth. All the oxygen you breathe was produced by the early organisms on life on Earth. That's one of the reasons why when we look for life on other planets, we're going to look for oxygen atmospheres, which isn't a guarantee of other life, but it'd be a strong signal, because it's important for the history of life on Earth that there was no free oxygen, because oxygen is a poison. It burns things. And if there had been, all the organic materials on Earth would have been oxidized early on, but they weren't. The life created the oxygen. And so these things puffed out little bits of oxygen, and over 2 billion years in the early history of life on Earth, the oxygen abundance built up until life figured out how to use oxygen by respiration. So every time you breathe in, you're not just breathing in atoms from Julius Caesar and everyone else, but also the atoms breathed out by these stromatoli over 2 billion years. You're connected to everything that's ever lived on Earth. You're connected to the stars, the planets, and everything that's ever lived on Earth. Okay. And in fact, when I talk about this, about what you're drinking when you drink in, here's another experiment you can do. Take your finger and prick it and take a little bit of blood and go out to the ocean and let a drop of your blood go in the ocean. Interestingly enough, if you come back a year later and take a spoonful of ocean water, there'll be some atoms of your blood in it. It gets distributed throughout the whole ocean. You are literally connected. So this is a quote from Shakespeare. That you remember in Macbeth, when they kill the king, and he says, "Will all great Neptune's oceans wash this blood clean from my hand? No, this my hand will rather the multitudinous seas incarnadine." In English, that means that I'll turn the oceans red. There's too much blood on my hands. And of course, it's true. Every time you bleed, if it goes in the oceans, you'll turn the oceans red in a very small way. So those connections to everything on Earth are remarkable and totally unexpected, I think. And I hope that gives you a different perspective of your place. But I want to point out now, I want to talk about a different set of connections. The kind of connections that relate you to things that are esoteric. The kind of physics I do is very esoteric, and people say, what good is it? And does it make a better toaster or a faster car? And it doesn't, but it does help. And I first began to think of this when I was stuck in Los Angeles, but the same could be said for coming here. So I flew in at about 11 o'clock today from the United States, and I came from the airport well, that's the hotel I'm in, but you shouldn't know that. Anyway, except for the beautiful women, they should all know that. No, but anyway, no. And so one uses GPS. And the good-looking guys, too, I guess. No, I'm just joking. Anyway, that's the problem of drinking before speaking. It's really a mistake. But, and the point is, every time you use your GPS, you're relying on remarkably esoteric laws of physics that you may not know. So how does GPS work? GPS works because there's a network of satellites around the Earth, and we use triangulation. So these satellites are way above the Earth, and what we do is, when your transmitter is detected by two different satellites, those satellites calculate the time that it takes for the signal to go from the satellite to the Earth and back. And from that, they can determine the distance to where you are. And when you have 2 of them, or 3 of them, or 4 of them, they can pinpoint your position. Sorry. And that's why we need to have several satellites in view in order to use GPS. Okay. So those 2 satellites measure the time it takes to get from there to there and back, and then very carefully, but they have to have very accurate clocks to measure your position very accurately, because light goes about 1 meter every billionth of a second. So if I want to know your position to 10 meters accuracy, say, then I have to have clocks on those satellites that are accurate to 10 billionths of a second. Atomic clocks can achieve that kind of accuracy, but we have to recognize that these satellites are out there. So light travels at 30 centimeters per nanosecond. That's 30 centimeters every billionth of a second. Now these satellites are up at and I'm going to use American units here, I'm sorry, but 12,000 miles above the Earth, most of them, and they're traveling around the Earth at 8,000 miles per hour. And this means that esoteric laws of physics matter. So to get an accuracy of 5-10 meters, 20 to 30 nanosecond accuracy. Now, relativity tells us that if I'm moving with respect to you, my clock is ticking slowly with respect to you. This is not observable on Earth most of the time. But if I want to measure things with an accuracy of nanoseconds, and things are moving at 8,000 miles per hour, I have to use this. And in fact, special relativity tells me that the ratio of the time of 2 clocks depends upon this, which is where this is the speed of the clock, and this is the speed of light. Normally, because we move very slowly compared to the speed of light, this is irrelevant. But in this case, it isn't. It turns out that these clocks, because they're moving around the Earth very fast, tick at a rate of 7 microseconds per day more slowly than clocks on Earth. But this isn't the only effect. Einstein also told us that if I'm standing up here, my clock is ticking at a different rate than your clock. Because being at a different place in a gravitational field also means clocks tick at different rates. And these clocks are up at 12,000 miles above the Earth. So general relativity tells me, if you plug things in, that in fact, because these clocks are this high, they're ticking, it turns out, 45 microseconds per day faster than clocks on Earth. Now, this means that they go in different directions, that these clocks are ticking relative to each other and relative to clocks on Earth at a time difference of 38 microseconds per day. But 38 microseconds is 38,000 nanoseconds. And that means if the makers of GPS didn't include the facts of the curvature of space and the effects of special relativity, things you'd never think you need to ever think about, then your GPS would lose accuracy in 2 minutes. In 2 minutes, it'd be out by about 1 kilometer. And so every day, in order to get here, or anywhere you go in your cars and use GPS, you're relying on the fact that space is curved. This esoteric result from general relativity that is remarkable. So even the most exotic aspects of physics creep in and change our everyday lives. Now, this is meant to hypnotize you. I'll take a drink while you're doing it. This hidden connection, the fact that you're connected to a curved universe, is something that we're using in physics nowadays in a different way. Not only is space curved, not only are clocks on these satellites ticking at a different rate, not only is my clock here ticking at a different rate than your clock there, but every time I move around this stage, I'm disturbing space. Because Einstein told us that space and time respond to the presence of matter and energy. And when I move around and wave my arms like I often do, I'm producing a curvature of space that's varying in time. And in 1916, Einstein realized when he wrote down general relativity that when I do this, I'm producing a moving disturbance and it causes a ripple in space. When I shake an electric charge up and down, I produce a disturbance in electric and magnetic fields that is responsible for everything in this room, the lights I see. Those come from that kind of shaking. Electromagnetic waves result when I shake charges up and down, and the electromagnetic waves produce light. That's how I see. But Einstein showed us that if I shake a mass up and down, I disturb space. I produce a disturbance, a curvature in space. And just like a ripple on a pond, that disturbance travels out, in this case at the speed of light. And what it means is every time I do this, I'm actually changing the space in this room. And I'm producing what we now call a gravitational wave. And that means, and there are tons of gravitational waves going through this room right now. And when a gravitational wave goes through this room, much as if it went through this screen, the length of the room gets smaller in that direction and larger in that direction, and then smaller in that direction and larger in that direction. And that's happening now. Those of you who've drunk a few of these notice this right away. But the effect is so small that we don't notice it. Why don't we notice it? Because gravity is the weakest force in nature. It's hard to believe that gravity is so weak because when you get up out of bed in the morning, you feel it right away. But that's all the atoms in the earth affecting a single atom in your body. But gravity is the weakest force, and Richard Feynman gave an experiment to show how weak gravity is. Take a friend, maybe not a friend, to the top of a high building. Push them off. It takes all of the atoms in the earth and their gravitational force to pull them all the way to the ground in maybe 100 meters, if it's a really high building. But electromagnetism stops them in a fraction of an inch. They don't even make a dent in the concrete. Because the reason I don't fall through this stage is not that it's solid, it's mostly empty space. But the electric forces of the electrons in my hand, or in this case my feet, are repelled by the electrical forces of the electrons in the stage. So just the electrical forces of the electrons in the stage are holding me up against the entire pull of the Earth. Gravity is so very weak. And that means the gravitational waves I create are so small, you'd never be able to see them. Here's a three-dimensional gravitational wave moving through. It looks nice, but it doesn't have any information. But those 3D images don't. But the point is, if this is there, we'd like to be able to detect it. If these ripples in space are occurring all the time, are they really happening? Or is this a figment of our imagination? And what amazes me is that we have built the most amazing machines to be able to detect these ripples in space. Here is a machine, the largest gravitational wave detector in the world, the LIGO, the Laser Interferometric Gravitational Wave Observatory. There's 2 copies of this. This is in Hanford, Washington. There's another one in Livingston, Louisiana. Exactly the same. And what these things are 2 arms, 2 perpendicular arms, each 4 kilometers long. And if a gravitational wave comes down from above, what will happen is the length of this arm will get a little bit smaller, and the length of that arm will get a bit longer, and then the length, then the length of this one will get smaller, and that will be longer. So all you have to do is measure the length of these two arms very carefully. Simple. Not so simple. Gravity is so weak that we calculate if the most cataclysmic event we can imagine happening in the universe today, the collision of two black holes, solar mass black holes, happening in our galaxy or some distant galaxy happen. Two massive objects, more massive than our sun, colliding, well, they'll produce a lot of gravitational waves because the more intense the gravitational field around the object and the more catastrophic the event, the bigger the gravitational wave signal. So we can look for two colliding black holes, solar mass black holes, but the effect is still very small. In fact, we can calculate that if two black holes collide in a distant galaxy, two solar mass black holes, gravitational waves will be produced, and they'll change the length of this arm relative to that arm by an amount we can calculate. These arms are 4 kilometers long, and in order to be able to detect this signal, we have to detect the fact that these gravitational waves will change the length of this arm, 4 kilometers long, compared to the length of this arm, by an amount equal to 1/1000th the size of a proton. Now that should amaze you. 1/1000th the size of a proton. What's even more amazing is we can do it. We can do it. And I'm not an experimentalist, and this is one of the reasons why, because I never would have figured you could do this. And in fact, it's really hard to imagine that you can do it, because if a truck hits a pothole over here, it produces a bigger signal here. So how can you get rid of that? Well, you build two detectors, one in Washington and one in Louisiana. And if a gravitational wave traveling at the speed of light hits this detector and goes through the Earth, 8 milliseconds later, it'll go through the detector in Louisiana. So what you look for is a signal in this detector and exactly the same signal 8 milliseconds later in Louisiana. And on September 15th, I think 2015, we saw the first gravitational wave ever discovered in the universe. This is the signal, and it's a signal of two black holes colliding in a galaxy 1.3 billion light years away, causing space to ripple and vibrate back and forth. It turns out with a frequency of about 300 cycles per second. That means these two objects, these two solar mass black holes, one was 36 times the mass of the sun, the other is 29 times the mass of the sun. They were orbiting each other 100 times a second before they collided. Think about that. Two solar mass objects orbiting each other 100 times a second. And what's amazing is not just that we could detect the signal, but we needed not just the most sophisticated technology available on Earth, because even the quantum mechanical motions of the mirrors are bigger than 1/1000th of the size of a proton, so we have to use what's called quantum optics to overcome that. But we have to use the most sophisticated theory we can do, because if you see a random bit of noise, how do you know it's colliding black holes? You have to have an expected signal to compare it to. And the mathematics of general relativity is very complicated. And we needed supercomputers. And over the last 20 years, we needed those supercomputers. Only 2 years ago did we have the technology in the experiment and the theory. And so this template, the sort of smoother line, is a template of what you'd expect if two black holes collided. And we can compare the signal to the template, and we see it's a beautiful fit. And this was the signal seen at Hanford. 8 milliseconds later, this was the signal seen in Livingston, and the two fit exactly on top of one another. And what we saw was a signal of two black holes colliding 1.3 billion light years away. And I'll show you the animation of this. This is not the visual. This is an artist's simulation. But you can see when these black holes are moving around, they're bending the space around them, and they're causing the light around them to be perturbed. So you're actually, the stars behind them look like they're moving because the space is curving. And this is a slowdown of the actual last 0.2 of a second in the life of these two black holes as they collide and merge to form a single black hole. And if you watch in the last moment, you'll see space jiggle, and that's the generation of gravitational waves. There, see it jiggle? Now, that's the signal we saw. Now the amazing thing, there's two amazing things about this. First, that we saw it. But secondly, it was a 36 solar mass black hole and a 29 solar mass black hole, and they combined together to form one single black hole. How massive was that? 36 plus 29. 36 plus 29. Anybody? Who said 65? Put up your hands if you said 65. Put up your hands. No, it was more than just you. Okay, you said 65? Wrong! Because it's amazing. It turns out they formed a black hole of 62 times the mass of the sun. 3 solar masses disappeared. Where did those 3 solar masses go to? Into gravitational waves. Now that may not amaze you, but it should. Because our sun is burning 100 billion hydrogen bombs every second to produce the light that we see. And it's turning mass into energy, E equals mc squared. Over the 10 billion year lifetime of the sun, less than 1% of the mass of the sun will turn from matter to energy. In 0.2 of a second, these objects turned 3 times the mass of the sun into energy. That meant during that 0.2 of a second, that object emitted more energy than all the rest of the stars in the visible universe combined. It's amazing that these things happen, and we detected it. Now, as amazing as that is, these are interesting gravitational waves, but the gravitational waves that are of interest to me are going to be looked at by a different machine. This is at the South Pole. We're looking for gravitational waves not from the collision of 2 black holes, but for gravitational waves that connect us to the beginning of time. We think we're here because of an event that happened when the universe was a millionth of a billionth of a billionth of a billionth of a second old. When our universe expanded by a huge amount someone's trying to call me right now. Hold on. Let me just stop that. Okay. We think at that time when the universe was a millionth of a billionth of a billionth of a billionth of a second old, our universe expanded by a huge amount, puffed up from the size of a single atom to the size of a basketball or soccer ball if you're here in Europe. In a short instant. Now, if 2 black holes colliding produce gravitational waves, if our entire universe expands like that, it'll produce gravitational waves that we hope we'll be able to detect one day. And this is a machine we're hoping to use to detect them, among others. This is called the bicep detector. It turns out that these leave an imprint. These gravitational waves, we think, leave an imprint in the microwave background radiation that's coming at us from the Big Bang, that's coming at us from all directions that we measured first 30 years ago and have now seen more seriously in various other ways. When we look out, we see this radiation coming at us from all directions. We call it the cosmic microwave background radiation that was emitted when the universe was about 300,000 years old, which is when it became transparent to radiation. And when we look out, we have pictures of the universe back at that time. But embedded in those pictures may be a signal of gravitational waves that have come at us from the beginning of time. And in these kind of detectors, we're looking for them. It turns out these detectors are at the South Pole. It's not cold enough at the South Pole to use them. We have to send down liquid helium to use these detectors because it's not cold enough. We send down that liquid helium in the summertime. Does anyone know why? When it's winter in Antarctica, it turns out you can't send planes down there. Isn't that amazing? When I first learned that, I was shocked. We don't send planes down to Antarctica in the wintertime. I mean, we can go to the moon. Well, that was faked. But we can go down to the depths of the ocean. We can go everywhere, but we don't send planes to Antarctica in the wintertime. That's why this is one of my favorite images. This is from the bicep detector, and it's at sunset. Sunset happens once a year at the South Pole. So it means if you take this picture, you're stuck there for the winter. Okay? Which is why this picture was taken by a graduate student. Okay? But it turns out that this detector and others like it that are being built may allow us to detect gravitational waves from the moment of creation, if you wish, connecting us to the process that produced ultimately all of the stars and galaxies we see today, a process we call inflation. And what's really kind of interesting is that we think that this process that caused our universe to explode in size actually caused space to continue to explode in most other places. Our universe basically was like a seed that condensed out of this rapidly expanding universe. But that expansion continues even today. And that means there may be other universes being created right now as other seeds collapsed out of that background expansion. And if inflation happened, then our universe isn't unique. There are many universes out there. And it turns out when you leave inflation, the laws of physics may change depending upon how you leave inflation. And that means some universes may form with a lot of galaxies, some universes may form with no galaxies, some universes may form with just the right number of galaxies. So it could be that all of the physics, the properties of our universe, are just one big cosmic accident. That in a different universe where the laws of physics would be different, we wouldn't be here. That makes it sound like the universe, well, it basically says the properties of the universe are the way they are because there are astronomers here to measure them. That sounds religious, but it's not. It's cosmic natural selection. Because it says that our universe is one in which we could evolve. It'd be fascinating to find ourselves living in a universe in which we couldn't evolve. That would be worth a book or two, but no one would be around to read it. And this idea of what's called a multiverse, when I first wrote A Universe from Nothing 5 years ago, was just a pure speculation, a well-motivated speculation, unlike God. But one that was pure speculation, metaphysics, if you wish. But what I find amazing is we're on the threshold of potentially being able to measure gravitational waves from inflation, which, if we could measure them, would tell us about that inflation happened, would allow us to probe that theory and see if indeed other universes are being created. We wouldn't be able to see them directly, but we'd be able to test the physics that created our universe and know indirectly that those other universes are there. Just like over 100 years ago, we knew atoms existed, but we never thought we'd see them. If this is true, we'll turn metaphysics into physics. We'll know indirectly that these other universes exist. And that we're not only not alone in our universe, but that our universe is not unique. And it amazes me to think that in my lifetime, we may be able to know that our universe isn't unique, that we are, in a sense, connected not just to all the stars in our universe in any way, but to other universes by that act of inflation. Now, this cosmic accident is similar, I want to end, with another cosmic accident, which is related to my new book in more detail. The greatest story ever told so far, relates to a fact that we are all here by another cosmic accident. There's a bathhouse here, and I wanted to go to it, but it's going to be closed now, so I can't. But let's say you're swimming in water, and you swim very fast. Fine. Let's say I filled that swimming pool with molasses. Well, you wouldn't want to get in, first of all. But if you did go in and you tried to swim, you'd swim much more slowly because the molasses would produce much greater resistance. Well, it turns out that we think that that's why we're here. That there is an invisible field everywhere throughout our universe that froze in the early history of our universe. And some of the particles in nature interact with that field, so as they move along, they experience a resistance. And they act more massive. Those particles interact more strongly with that field or more massive. Those particles that interact less strongly with that field are less massive. And those that don't interact with the field at all are massless. Light doesn't interact with that field. But at a fundamental level, all the particles that make us up are really massless. They act like they have a mass because that field is there. Now, that sure sounds like religion, right? Because what I said was, there's an invisible field everywhere in the universe, and it's the reason we're here. And that would be religion, but it's not religion because we can detect it, or we can try and detect it. How do we try and detect it? Perfectly in keeping with the video at the beginning of this program, cosmic sadomasochism. We spank the vacuum. We spank it hard. Because it turns out in quantum physics, for every field in nature, there's associated with a particle. And if we take enough energy and dump it into empty space in a single place, we'll take that field and we'll kick real particles out of it. And if we call that field the Higgs field and we kick real particles out of it, we'll call them Higgs particles. So where can we dump enough energy and empty space in a single point to kick out Higgs particles? How can you do that? You create the most complicated machine ever built, the Large Hadron Collider in Geneva, Switzerland. You go to Geneva, and there's the lake. The fountain is over here. If you land at the airport, which is right here, which I did a little while ago, you look out and you see just countryside, beautiful countryside. But underneath the countryside is a tunnel 26 kilometers around. And in that tunnel, we accelerate particles at 99.9999998% the speed of light in that direction, and particles at 99.9999998% the speed of light in that direction, and we try and collide them in a few places. This is the French-Swiss border right here. They go around thousands of times every second without passports. Don't tell Donald Trump, he'll be upset. But we then try and collide them, and in fact, July 4th is a big day in the United States for no real reason, but in no cosmic reason anyway. But July 4th now has a cosmic reason for celebrating, because on July 4th, 2012, the Large Hadron Collider reported 50 events that walked like Higgses and quacked like Higgses, and therefore we thought were Higgs particles. And in fact, in the intervening 5 years, all the data has told us that they have exactly the properties of Higgs particles. We've discovered that there's an invisible field in the universe, and that this amazing story that we're here because of that invisible field is really true. I mean, it was so amazing that I was certain it was wrong. I'd written 3 papers, which I had in my drawer waiting for it not to be discovered, so that I could show it was wrong, because I thought nature would find another way to do it. It seemed kind of slimy to have this invisible field everywhere. But that's exactly the kind of invisible field that could have produced inflation. So it gives us further motivation to think that inflation happened. But that means that we are here by a truly cosmic accident. If you look at in the wintertime in a window, and look at the icicles on a window, say this icicle here. Imagine that you were a civilization that evolved on that icicle, that grew up in that icicle. There'd be physicists, and they discovered the laws of physics are different along the spine of the icicle than along the perpendicular direction, and they described those laws. Theologians would explain why that direction was special, why it was meant by God. Wars would be fought over whether it was that direction or that direction. All of this would take on an incredible significance. But seen from the outside, we see it's just an accident. Icicles can form in all different directions. It's just an accident. Our existence here in the universe is the same kind of accident. If this Higgs field hadn't frozen the way it did in the early history of the universe, and had frozen in a different direction, the forces and the laws of physics we feel would be different. And in fact, we wouldn't exist. But imagine that physicists on this ice crystal figure out that, there's nothing special about this direction, that all sorts of different directions could exist. And they figure it out at 4 in the morning. And at 6 in the morning, the sun rises and the ice crystals melt. And they go away. That could be us. Because we've discovered the Higgs field, but we've also discovered, given the properties of that field we've measured, it could be unstable. It could melt in the future. And if it melts in the future, then all the particles that now have mass will become massless again. And that means no structures will exist. All the stars and galaxies and everything that we feel connected to will disappear. And that could be our future. Don't get too nervous. Don't sell your diamonds, because even if this were to happen, and we're not sure it would happen, it won't happen in a year or in a decade or in 1,000,000 years or 1,000,000,000 years or 1,000,000,000,000 years. It'll happen in the far future. But in the far future, the universe could return to the state it was originally in, one that was not, in which life as we now see it was not possible. So those people who think the universe is designed for us, it's no more designed for us than that direction is significant. We are a cosmic accident. And that's okay. That's remarkable. We should feel thankful. The universe isn't any more designed for us than it was designed for that crystal to exist in that direction. This idea of understanding that the universe is not necessarily the way we wanted it to be is humanity at its best. One of the wonderful things about being here, besides being with all of you and in this amazing venue, is this connection between art and music and science that's happening right here tonight. Because that's the beauty of science. It's not the technology. I mean, science creates technology, but I almost think of it as an unfortunate thing, because the real beauty of science is the same as the beauty of art, music, and literature. What science does is change our perspective of our place in the cosmos, change our understanding of ourselves. That's what we get when we read a good play, or see a piece of art, or hear a new piece of music. It forces us to reflect on ourselves in a new way. That's the beauty. And to force our beliefs to conform to the evidence of reality instead of the other way around is wonderful. To take cherished beliefs and prove them wrong is wonderful, because it means we're learning. And that's what makes civilization worth being called civilization. The fact that the universe isn't designed for us has a long history. And I want to end by just going back to the person who first showed, in the context of life, that the universe wasn't designed for us, Charles Darwin. One of the most beautiful bits of science writing in all of science writing history is the last paragraph of his Origin of the Species, that reads as follows: "There is grandeur in this view of life, with its several powers having been originally breathed into a few forms or into one, and that whilst this planet has gone cycling on according to the fixed law of gravity, from so simple a beginning, endless forms most beautiful and most wonderful have been and are being evolved." In that beautiful way, he showed how from a simple beginning, the incredible diversity of life on Earth could arise, not by planning, but by natural selection. Bees aren't designed to see the colors of flowers. If they didn't see the colors of flowers, they couldn't reproduce. They couldn't get the nectar and reproduce. It's so simple to see something that looks like it's designed. The appearance of design can be an illusion. And not just as it's true for life, we now see that even for the universe, the appearance of design is an illusion. Just get over it. But at the same time, science changes, and scientists themselves are myopic. And in 1863, he said in a letter to Joseph Hooker, "It is mere rubbish thinking at present of the origin of life. One might as well think of the origin of matter." Now, in 1863, that was garbage. But I get paid to do it now. Because things have changed. Because the greatest story ever told has gotten better because we keep opening our eyes to the universe. We keep getting surprised by the universe. And we'll keep on getting surprised by the universe. And being human will continue to be more interesting, but only if we keep our eyes open. Only if we're willing to keep asking questions. And if we stop asking questions, if we're afraid of what we'll learn, if we're afraid of others, all of that will stop. And while it's an issue in my country, I think it's an issue more generally. I am concerned in the current world about this fear of the unknown, about this fear of others, about this fear of what science may tell us, and that people would rather bury their heads in the sand and not support not just science, but art, music, and literature. And the response to that is, the best response to that I know is by this guy, Robert Wilson, who is the first director of the first large accelerator in the United States, the first really big accelerator, the Fermi National Accelerator Laboratory. In the 1960s, he was asked by Congress, will that accelerator aid in the defense of the nation? And he said, "No, sir, I don't believe so. It has only to do with the respect with which we regard one another, the dignity of men, our love of culture. It has to do with are we good painters, good sculptors, great poets. I mean, all the things we really venerate in our country and are patriotic about, or should. It has nothing to do directly with defending our country, except to make it worth defending." And that, you can applaud to that because he's dead now, but it's a wonderful line. That is why we can't afford to stop supporting curiosity-driven science research. We can't afford to stop supporting art, music, and literature. In my country, the current budget, there's huge cuts in all of that. And the money is going to build a wall to keep us out from invisible hordes. But what makes the United States great, what makes Denmark great, what makes the world worth living in is not the walls we build or the arms we sell, but the questions we ask and our willingness to keep open eyes and look at the universe. So the universe may be miserable, we may be insignificant, but we shouldn't be depressed. Because those connections that we've made to the cosmos tell us that that amazing accident that brought us here today nevertheless has allowed us to evolve brains that can ask questions, that can turn and ask questions about the early beginnings of the universe and look out to the farthest elements of the cosmos. So instead of being depressed, you should enjoy your brief moment in the sun. Thank you very much. Thank you. Thank you.